Good morning, S3. Today we're going to start our new chapter of work, which is all about similar shapes. We need to begin by thinking about the idea of enlargement and reduction. If you look at the two pictures to the left there, the two chess pieces are mathematically similar. This means that one is an enlargement of or a reduction of the other. We can see in this case that shape 2 is a reduction of shape 1, and shape 1 is an enlargement of shape 2. But very often we want to be able to look and say, well, how much of a reduction or how much of an enlargement is it? To do this, we can use the lengths of the sides which are marked on the shape. So if you look at shape 2, you can see its height is 4 centimetres. The height of the first shape is 8 centimetres. So we can say that shape 2 is a half of the size of shape 1. But it has to apply to the length going across the way as well. So we've got 4 centimetres, a half of the 4 centimetres is 2 centimetres. That is called the scale factor. And so what we can say is that the scale factor of the reduction is equal to a half. And that's because shape 2 is a half of the size of shape 1. Going the other way, we can see that shape 1 is an enlargement of shape 2, but how much of an enlargement is it? Well, we can see that the lengths are double the size. So the scale factor of the enlargement is equal to 2. Example 2. Let's look at these two shapes. The shape is a trapezium. It's got two parallel sides. That's what makes it a trapezium. And we can see that shape 2 is an enlargement of shape 1. And if we look at shape 2, we can see, well, if we compare all the lengths that we know, we've got 3 centimetres becoming 9 centimetres. We've got our 2 centimetres diagonal side becoming 6 centimetres. And we've got that 1.5 centimetres and we've got a missing side. So we start to see where we can go with this. We know that shape 2 is an enlargement of shape 1. And again, we can add in the scale factor. So if we look at our scale factor, the scale factor of the enlargement is how much bigger is shape 2 compared to shape 1. So comparing the sides that we know, the 3 becomes the 9, the 2 becomes the 6. We can see that we've multiplied by 3, so the scale factor is equal to 3. And that allows us now to move on and think about a little definition. And two shapes are said to be mathematically similar if one is an enlargement or reduction of the other. And this must be true for all corresponding sides and angles. And by corresponding angles, we mean that if we look at this shape here, the angles in corresponding positions are the same size. So this angle here has got to be the same size as this one here. This angle up here must be exactly the same size as this one up here. This one here and this one here are exactly the same. And if we put a little x down here, this angle here and this angle here are exactly the same. So it's all of these things that make a shape or make two shapes similar to each other. The corresponding sides and corresponding angles are in the same, well, corresponding angles are the same, corresponding sides are in what's called the same ratio. Using what we already know, can you work out the length of the missing side x centimetres above? Well, if my scale factor of my enlargement is 3, my 1.5 multiplied by 3 tells me that x must be equal to 4.5 centimetres. And that gives us a little flavour of where we're going next with this idea. So we have our two cars in example 3. We're told that they are mathematically similar. So if they're mathematically similar, then the ratios of their sides have got to be the same. So they've got to be, one's got to be an enlargement or a reduction of the other. Part A of the question says calculate the scale factor of the enlargement. So how much bigger is the second car compared to the first. So in part A, in fact I don't want to use that colour, so I'm going to take that away. I'll change my pen. So part A, the scale factor of the enlargement, and I'm just going to denote that by SF now. Well, you can work it out really easily by looking at, well, the big side over the small side. Okay, so we can see it's 120 over 30, they are corresponding sides, and that simplifies down quite nicely to 4. So the scale factor of the enlargement is 4. The big car is 4 times the size of the small car. And we can use that in part B to work out the height of the larger car. Now there are 2 ways we can do it. We can do it by saying, well, if the small car has got a height of 25 centimetres, the large car has got to be. So in part B we want to calculate the height of the larger car, so we want to calculate the size of y. And we know that the scale factor of the enlargement is 4, so y must just be equal to, again getting mixed up with my pen colours, y must be equal to 4 times the length of the side that we know. And 4 times the length of the side we know is 4 times 25, which is equal to 100 centimetres, which is equal to 1 metre, because there are 100 centimetres in a metre. There is another way where we can do this, comparing the ratios of sides, and this method becomes more helpful as we move through this chapter. And what we can do is we can say that, well, we can compare the ratios of sides, so we can say that y over 25, they are the corresponding sides, is equal to 120 over 30. And then what we can do is we can use the method of cross multiplication. Now with this example it's very simple to use the first method, but just to get you used to thinking about it in this way, because we're going to need that later, what we get is that 30y is equal to 120 times 25. It's early in the morning, so I'm just going to use my calculator to work that out. So it comes out to 3,000. So y is equal to, and again we know that we can just simply divide both sides. And we get that y is equal to 100, exactly the same as for above. And you might be thinking, well, why would you use that method, because that seems more complicated than what we've already started with. This method becomes more important later on when we're actually comparing the ratios of sides, and you'll see that as we move through this chapter. Very often this will be the preferred method, but for now we can simply use the scale factor. 30. Oops. So note that the scale factor of the enlargement or reduction is also known as the linear scale factor, linear meaning lines. So we're very often looking at lines in these examples in order to work out our linear scale factor. Example 4 here, the 2 squirrels are mathematically similar. Calculate the linear scale factor of the reduction, and then calculate the height of the second squirrel picture. So in part A, if we look at it, the scale factor of our reduction, our linear scale factor, is equal to, well, we can put, it's a reduction, so it's the small side over the big side that we know, so it's 1.5 over 9. And what we find is that that comes out to give us 1/6, I think, 1.5 over 9. 1/6. And then we can use that linear scale factor in part B to work out what the height would have to be. So the height has got to be equal to 1/6 of 12, which is equal to 2 centimetres. Using our alternative method, we can say h over 12 is equal to 1.5 over 9. And then if you were to carry out cross multiplication, we can work out, we'll find that h is equal to the same. H is also equal to 2 centimetres. We get 9h equals 1.5 times 12, which is 18. So h is equal to 2 centimetres. So you have a choice of methods that you can use today. What I would like you to do is have a go at some of the questions in the textbook. The questions in the textbook tend to use the linear scale factor method, but you have a choice of methods you can use there. So what I would like you to do today is, let's get a pen. So it is textbook page 48 and 9. Exercise 5.1. Questions 4 to 11. And don't forget to mark your work. Okay? It's really important to keep your notes jotted up to date, so remember you can stop this little video at any point in time. Third year, I hope you have a good day. See you all soon. Bye.